Non-segregated and segregated phase bus are also called bus ducts. Introduction. Air-insulated live conductors, supported on insulators and enveloped in a common metal enclosure, are the earliest forms of bus duct. Even today, this principle governs most power connections in low and medium voltage applications up to a system-rated voltage of 36 kV. The bus ducts are designed and manufactured not only for AC, three-phase or three-phase with neutral power connections, but also for six-phase AC connection between rectifier transformer and rectifiers and a two-pole DC connection. Line-to-ground faults are common in a power system. In medium voltage systems, the neutral of the transformer is grounded through a resistor to limit the line-to-ground fault current. All generator neutrals are earthed either through a resistor or by a combination of neutral grounding transformer and neutral grounding resistor. Bus duct has earthed metallic enclosures. An arcing fault will ionize the air in the vicinity, and depending upon the intensity of ionization and time, the ionized gases can spread to the neighboring conductor, resulting in a phase-to-phase or even a three-phase fault. If the ionized gases due to arcing can be confined to a limited area by the introduction of a phase barrier between the two phase conductors, then the probability of a ground fault developing into a phase-to-phase or a three-phase fault can be minimized. Installation of the phase barrier can increase the factor of safety to a considerable extent. If the intensity of the arcing fault is high, the arc may penetrate through the barrier and initiate in a phase-to-phase or a three-phase fault. The shape of a bus duct enclosure can be either circular or rectangular. Bus duct for three-phase four-wire systems has only a rectangular shape. Bus ducts are broadly classified as non-segregated phase bus and segregated phase bus. A non-segregated phase bus houses all the phases and neutral in case of low voltage conductors in a common housing with only air insulation between the phase conductors and between phase conductors and earth. A segregated phase bus also houses all the phase conductors in a common housing, except that each phase conductor is segregated from the other phase conductors by an earthed metallic or an insulating barrier. Air is still the primary insulation for the conductor. Phase barrier is provided to reduce the probability of a phase-to-phase fault. Phase segregation in a low-voltage system is rare. Description. Bus ducts are custom-built products that are required to be manufactured in a factory and installed at the site. Few non-segregated phase bus of relatively lower current rating, busbar trunking, that are installed in assembly shops, factories, and commercial complexes, can be put together at the site with standardized factory-built assemblies with minimum customization. These are for secondary distribution. Major components of a bus duct can be broadly categorized as conductor, enclosure and canopy, insulators and bushings, segregation, bus duct accessories. Conductor. The conductor material is either copper or aluminium. In general, conductors with a rectangular cross-section, large width to thickness ratio, and in the vertical orientation make the rectangular bus ducts efficient and compact. This is adopted by most of the manufacturers of low-voltage bus duct. For low-voltage bus duct with copper or aluminium conductor, it is prudent to use a single bar per phase up to its maximum current rating, with the same size for the neutral bar. If it is not feasible to achieve the desired current rating, 2 bars per phase and 1 bar for neutral may be installed. There are applications such as in data centers where the magnitude of the neutral current can be higher than that of the phase current due to the presence of harmonics. The cross-section of the neutral bar may even be more than that of the phase bar. The width of the bar, for both copper and aluminium, is usually limited to 300 mm or 12 inches, and the thickness to 12 mm or ½ inch. In medium voltage bus ducts, copper or aluminium conductors extruded or formed in the shape of a channel are also used. Such shapes help increase the section modulus to enhance the load withstand capability of the conductor, lower skin effect ratio, apart from providing more cooling surface area. Flat conductors of large dimensions are supported in a vertical orientation. The support facilitates the sliding of the conductor, both at the top and at the bottom. Single channel or double channel in box formation when used are supported by a single post insulator with provision for axial movement. Some specifications permit the conductor to be insulated, coated with an insulating material or sleeved, to decrease the air clearances, as long as all the electrical stress tests are successfully complied with, and consequently make the bus duct compact. Insulated conductors are more relevant to medium voltage than low voltage bus duct. The percentage reduction in the cross-section of the bus duct with the insulated conductors increases with the increase in the system voltage. For insulated conductors, the site joints need custom-designed seal boots for the configuration and voltage rating. In the absence of insulation, conductors are usually painted or coated matte black or dark shade for better heat dissipation. Enclosure and canopy. The enclosure material is either steel or aluminium. Stainless steel has been used for very specific applications such as in the pharmaceutical industries. Canopy, when installed as a weather or sun shield, is fabricated with steel or aluminium alloy sheets. Bus ducts with steel enclosure necessarily has to run an earth conductor of adequate size, supported from the enclosure, parallel to the phase conductors. Bus duct with aluminium enclosure need not be provided with an earth conductor, if the enclosure itself meets the minimum cross-sectional requirement for the envisaged earth fault current. Aluminium must be used as enclosure material for a current rating above 2000 amperes. Material of the canopy, installed in the outdoor sections of the bus duct, should preferably be fabricated from aluminium alloy. Aluminium extrusions are extensively used for the side rails and supporting or load-bearing members of the enclosure. Aluminium sheets and extrusions are available in various alloy forms and tempers to meet specific requirements. The enclosure shape can be circular or rectangular depending upon the system and project requirements. Circular shape. Based on theoretical consideration, the circular shape of the enclosure is ideal for a three-phase, three-wire system. From the very nature of construction, it is evident that the field distribution will be uniform. Consequently, the bus duct will be most compact for a specified basic insulation level. The steady-state electrodynamic forces, on a three-phase fault, will be identical on all the three phases. The temperature distribution will be almost identical for all the three-phase conductors. The induced enclosure losses due to the conductor currents will be minimal as the magnetic field will rotate around the enclosure. Enclosure current density will be uniform. Since the configuration is symmetrical, the voltage will remain balanced along the length of the bus duct. Phase transposition is not required for balancing the voltage. Since the construction is simple, it is easier to obtain the desired degree of protection. A degree of protection up to IP65 is not difficult to achieve. It is ideally suited for higher current ratings of long lengths. Because of the rigid nature of the circular enclosure, larger enclosure support spans can be adopted. This configuration is ideally suitable for medium voltage bus duct of longer outdoor lengths where factory-built, long sections can be assembled. This would make the installed bus duct cost-effective. The circular enclosure design is more compatible with a tubular conductor as any change in the direction in the run of the bus duct can be easily negotiated. It need not be restricted to a horizontal or vertical plane as in the case of a rectangular enclosure. Circular enclosure expansion joints are cheaper and easy to install. On a three-phase short circuit, the force on the conductor will cause it to undergo a rotary motion, not an oscillatory motion, at twice the system frequency. However, on a line-to-line fault, the conductors will be subjected to an oscillatory motion at twice the system frequency. For a circular conductor, since the section modulus is the same for any radial axis, the stress and deflection will be uniform and proportional to the force. It is not economical to manufacture short runs comprising several bends as encountered in an indoor connection since incorporating bends and terminations is expensive. It is generally not suitable for LV bus duct since they tend to be of a three-phase four-wire system. The bus duct with circular enclosure and conductors in delta formation have to interface with transformers or switchgear with rectangular flanges and inline conductor configuration. Its engineering and manufacturing cost can be high. Rectangular shape. Despite several apparent advantages of a circular enclosure, the rectangular shape seems to be more popular and constitutes a bulk of the market. The reasons for this are not far to seek. Most of the bus ducts are required for the low voltage, three-phase four-wire system. The lengths of the low-voltage bus ducts are small since, in most of the layouts, the transformer is kept as close to the panel as is practically feasible. Almost all switchgear and transformers have rectangular flanges with inline terminals for an interface. It is easier to interface with a bus duct with a rectangular cross-section and inline terminal arrangement. For indoor installation, the section length of most of the bus ducts is small since they have to be negotiated and installed in a constrained space. Rectangular bus ducts are more cost-effective for such applications. Low-voltage bus duct with flat conductors in vertical orientation tends to be very compact in a rectangular configuration of the enclosure. Segregation. The segregation material is either an aluminium or an insulating sheet. An aluminium sheet is preferable. Mild steel cannot be used as a segregation material, especially when the enclosure material is steel, as it will form a closed magnetic loop. Mild steel will generate hysteresis losses apart from eddy current losses. An insulating material is used when there are constraints on the overall width of the bus duct. Glass-reinforced plastic with high surface resistivity is normally recommended. The surface should be smooth to prevent the accumulation of dust. The segregation material should be non-hygroscopic and fire retardant, with a good tracking index. The thickness of segregation is normally 3 mm, 1/8 inch. Insulators and bushings. The industry has standardized on the type and material of insulators and bushings for the support of conductors in low voltage and medium voltage bus ducts. Dough-molded compound, sheet-molded compound, or glass-reinforced epoxy or polyester resin sheets and pultrusions are used for low-voltage bus duct. Mechanical strength is the most important criteria. Cast epoxy resin and porcelain, insulators and bushings are used in medium-voltage bus ducts. The dielectric properties are the primary criteria. Insulator fixing in enclosure and conductor mounting or clamping on insulators varies depending upon the designs adopted by manufacturers. Bus duct accessories. A bus duct connection requires several accessories comprising enclosure expansion joints, conductor expansion joint, sleeves and seal boots, breather drain, disconnecting links, fire stops, space heaters, support structure. All these accessories need to be sized based on the rating of the bus duct and project requirements. Popular configurations. Many conductor configurations for a bus duct are possible based on the shape of the enclosure and profile of the conductor. Bus duct needs to be compact, and over the years, the industry has standardized on a few configurations for practical reasons. For medium voltage bus ducts, tubes and formed conductors are the preferred choice for the circular enclosures. And flat and formed conductors are the preferred choice for the rectangular enclosure. For low voltage bus ducts, flat conductors mounted between two insulating supports has been universally adopted because of ease of manufacture and flexibility. Thank you. Mr. Balachandran graduated with a bachelor's degree, B.Tech, in electrical engineering from the Indian Institute of Technology, Madras, India, in 1967, and obtained a master's degree, M.E., in power engineering from the Indian Institute of Science, Bangalore, India, in 1970. He is a Fellow of the Institution of Engineers, FIE-India, Fellow of Institution of Engineering Technology and Chartered Engineer, FIET-UK, and Life Senior Member of the Institution of Electrical and Electronics Engineers, IEEE-US. He was the Founder Director of Power Gear Limited and Busbar Systems, India, Limited. He has worked in manufacturing industries in India and the UK and is currently an advisor. He has engineered several busbar systems that have been manufactured and installed in various countries, including isolated phase bus for the largest hydroelectric power plant, 26 by 800 megawatts, at the Three Gorges project in China. During his professional career, he has developed and tested a range of bus products and their accessories. His area of interest also includes switchgear, instrument transformers, and power system analysis. The book, An Introduction to Busbar Systems, authored by V. Balachandran, is case-bound, hardcover, size A4, 386 pages, printed on 100 GSM glossy paper. Copies of the book can be purchased with a requisition to Bala at busbarsystems.net. Black and white version of the book is for sale in India, Afghanistan, Bangladesh, Bhutan, Nepal, Pakistan, and Sri Lanka at a cost of 4,500 Indian rupees plus freight. Color version of the book is for sale in all other countries at a cost of US $126.00 plus freight.